Good. All right. I do not a cent. Okay. I'm sorry for doing this, but we're going to start off with a quiz. All right. I know that's not what you sign up for. Question number 1. Are these birds? See? All right. Turns out you got that one right. Question number 2, is that a bird? That's a good start. Question number 3, here's a South American question. Are these birds? Well, they are. All right, so you did great. My question to you then is, how'd you know? So you got the questions right. You recognize birds. How did you know that they were birds? What traits did you use? Feathers, wings, 2-legged wings, beaks, general shape of them. Sitting in a tree.
That's true. That's true.
Okay, so let me just stop you right there. So I'm going to stop you right there. Okay. So those were all good ones, and obviously you used it to get the right answer. If we would consider like a deeper anatomical consideration, there might be other things we name like a wishbone. You know, Thanksgiving coming up, I figured I'd throw that out there. That's fused clavicles. So your collarbone, your clavicle, you stick them together and make one, that's a furcula. This keeled sternum, I mean, not to, just birds fly and that's cool. I'm not that impressed because my sternum ends here. If my sternum came out to here and I had chest muscles out to here, you know what, when I did this, things would happen. So like, yeah, they fly, but you give me chest muscles out here and I would do some cool stuff too. So they have a keeled sternum. They have all of these bones fused. They have a toothless beak. They have 3 toes that point forward, 1 toe that points back. They fuse so many bones that they stick some bones together to make a carpometacarpus, carpal bones in their wrist and metacarpals fusing together. They fuse the tip of their tail. They fuse, parts of their hip and their vertebral column. So we could go through all of these traits we use to identify birds. But there's really only one that I named that's actually accurate. Because a lot of the things that I have said, or maybe we have said, the first birds did not have. So we can't say this is what you need to be a bird if the first birds didn't have it. Or a lot of the things that have been named are things that dinosaurs had as well, at least some of them. So if you include not only the things alive today, the things which were alive in the past, the first birds and the dinosaur relatives. And I asked you, how would you identify a bird? It's actually a very hard question. And there's maybe only 1 or 2 things, and one thing isn't an absolute, you have it or you don't, it's a ratio type of thing that makes a bird. So when we talk about birds, birds are not as unique as we think they are. Like, I like birds, but let me just say, I'm going to start with the evolution of birds. I'm going to go back to the first reptiles. Now, why would I do that? Well, let's just, take arm muscles, for example. And you start dissecting things, and there's a salamander, or there's a frog. Look, the frog has a triceps. Look at the turtle. It has a biceps and a triceps. You look at, the alligator, biceps, it's got a shoulder muscle called a supracoracoideus. But then when you look at birds' wings, or like what you eat when you eat wings, what are you eating? A biceps brachii, a triceps, a deltoid, the same supracoracoideus that the reptiles would have. So the reason I want to start off with reptiles is it wasn't that birds invented muscles to fly with, for example. They just used the muscles that were already there in a new way. So with the history of birds, we start a little before the birds. All right, we start with the late Carboniferous period. All right, and if these people were to sing, and let's have them sing because that was actually requested. So welcome, Natasha. So if we were to look at the amniotes, now amniotes include birds, but they also include me. All right. What defines them? Well, one thing is before there were amniotes, there was a whole lot of sex going on in the water. All right. But that's a problem if you live on land. So even these things like water snakes, obviously water snakes are comfortable with land. They don't go in the water to have sex. They have it on land. And to manage that, they change the reproductive system. So amniotes, the males have a penis, the females can have a clitoris. These were amniote inventions. Nothing that isn't an amniote has those structures for internal reproduction. Their eggs can be laid on land because in addition to the yolk sac that things like fish can have, they have an amnion, a chorion, and a allantoid. So they have membranes around their embryos. We humans have them, so do birds, as we know from chicken eggs. And so these back to the very early amniotes. And then there's a whole bunch of other things we could talk about, like strengthening the vertebral column, et cetera. But when reptiles first appeared on land, they then had a number of traits which would be very important for the early birds as well. And somewhere, and really, I'm gonna, okay. And another thing that they started doing was to put holes in the skull for a variety of reasons, including for jaw muscles. So you have holes, all right? So you have holes in your skull that a lot of people don't think about. They're called the synapse openings. And so the first synapses had it there. But if you were to look at your skull, oh, look at that. There's a hole for jaw muscles. All mammals have one. But another lineage of reptiles, they did two. So they said, aha, a hole there and a hole there. All right. So these are the diapses, which would give us, among other things, crocodiles, dinosaurs, and the early birds. Another hole that would open would be here in front of the snout. So when we look at birds, this is a dinosaur, or actually this is an ancestor of a dinosaur head. But in addition to an eye socket, there are two holes here in the temporal region for jaw muscles, and there's a hole in front of the eye. Birds will have those as well. So once again, a lot of the bird features begin long before birds. Jump ahead to, okay, I'm sorry, I got too many things going on. Yeah, there's probably one more. I want. Let's talk about then the first dinosaur. So Carboniferous is when the first reptiles appear. And then there's mass death at the end of the Permian. More than 90% of life dies out. And then when we wake up, it's the Triassic period. We get the first dinosaurs. So let's talk about them. Now, really, I'm setting the stage for birds. This isn't, it sounds like I'm talking about dinosaurs, but we'll see why this is important in a little bit. One of the things that always makes me think is, here's the hip region of Tyrannosaurus rex. Where are the thigh bones? So let me ask you a question. Is that a thigh bone? Yes or no?
No, that's part of it.
Okay. We have some, is this a thigh bone? Is this a thigh bone? Okay. Right. So we'll hit a leg. But I kind of like the answer, I can't tell. But that's weird. Like if you look at a human skeleton, the thigh bones are the thigh bones. All right. Whereas this is weird. You've got these are what we call our hip bones. This is the ischium and this is the pubic bone. Now, in us are these little things that attach some muscles, but in dinosaurs, they become really big for really big leg muscles, all right? Dinosaurs are not just bipedal in the way that a dog can run on its hind legs, or, you know, in a circus, you could see maybe like a bear walk on its hind legs. Dinosaurs are good at it, like we are. And look at all of this. I mean, because you have like this tiny pubic bone, you have this tiny ischium bone. Theirs are as long as their thigh. So imagine that. Imagine your T-Rex. Your pubic bone, where your adductor leg muscles attach, is longer than your thigh. Your ischium is almost as long as your thigh. Just imagine what your leg muscles would look like. All right, you're already good at walking upright, but imagine you had that much leg muscle. All right, so dinosaurs, they get really good at walking on their hind legs. That's important for birds. The only way you can modify your arms to be wings is if you're walking on your hind legs. If you need your arms to run around like a lizard does, these don't ever become wings. So being bipedal, that's a precursor to flight. But the rest of this leg is kind of weird too. So here I have a question for you. We look at this bird. Do your legs bend like that? Yes or no? Very good. Ringers in the audience. All right, very good. Yes, your legs bend like that. Right? Now, if you're looking and saying, I don't think so, that's because you're not looking at this right. That is not the thigh. That's the thigh. It's kind of hidden by a lot of the feathers. The thigh is kind of short. That's the lower leg. That's the ankle. I know it looks like the knee. It's not. That's the ankle. And then this whole thing is the foot. So when you look at Tyrannosaurus rex, actually, its leg is a lot like yours. There's a thigh bone. The knee is pretty high. There's the lower leg, and there's the ankle joint. It's just that its foot is really long, and it's walking on its toes. All right? This bird's the same way. There's the ankle. This is the foot compared to us. Now, I have some videos on this, if you don't mind. So if we were to say, all right, let's look at a dinosaur leg, and specifically the meat-eating dinosaurs called theropods. Let's look at their legs, all right? So one, they've got this long pubic bone, this long ischium bone. You don't, all right? So there's your pubic bone, there's your ischium. They're kind of short, right? So you have the same bones as T-Rex, but you just don't have them project very long. But the very first dinosaurs, as they adapt to being bipedal, have this long process on the pubis, long process on the ischium. T-Rex has that. Now, the very first meat-eating dinosaurs, the pubic bone goes forward. And that's actually kind of a big deal because when we split the dinosaurs into two big groups, one of the groups is called the Saurischian group, which in Latin means lizard hip. All right. It's named so because the pubic bone goes forward. The other dinosaurs are called the ornithischians, where the pubic bone goes backwards. Okay. If we were to look at the hip of an emu, I'm going to give a true story shout out to one of our instructors here, Dr. Z. I went bird watching with Dr. Z once. You know what we found? An emu. He's that good. Kind of in High Point State Park. It got away from a farm and was killed by the side of the road. But in any case, here's the emu with it's a primitive bird compared to those alive today. But look, here's the very long pubic bone. Here's the very long ischium. Unlike most meat-eating dinosaurs, however, the pubic bone in most meat-eating dinosaurs juts forward. Here it curves backward. Things like Velociraptor would have this too. So T-Rex, it went forward. The first meat-eating dinosaurs, it went forward. But in Velociraptor, Deinonychus, and its cousins, it goes backward. But we see that this is essentially a dinosaur hip. Another giveaway is dinosaurs were weird in that they had a hole here in their hip socket. Their hip socket is hollow. That's weird. That was a dinosaur thing. Also a bird thing. Bird hips are modified dinosaur hips. And so once again, the early dinosaurs, as they modified their hip, so the acetabulum is open. We could talk about the ankle. This is going to be like a quick synopsis. I'm not going to try to stuff all of the comparative vertebrate anatomy of birds in there. But one of the other weird things, I'll get to the question in just a second. In your ankle joint occurs above a bone called the talus, and your calcaneus, your heel, is beneath it. So in you, the ankle bone is above this. But in dinosaurs and in birds, those two bones, like in you, the ankle would be here. In the ancestors of dinosaurs and birds, these bones stick to the tibia and the fibula, and the ankle joint occurs beneath them. So the first dinosaurs, they do a lot of crazy things with their legs. That's an important thing about being a bipedal dinosaur, the modifications of the leg. The foot gets really long, so you're only walking on your toes. Your ankle is actually occurring below those bones here, all right? And if you were to look at, T-Rex, we could name all of these things, and you could say, wow, that's a weird foot. Crocodiles don't have a foot like that. I don't have a foot like that. The dinosaur foot, well, that was odd. But you know what? If we compare it to a chicken, there's the femur on T-Rex, there's the femur. Here's the tibia and the fibula, there's the tibia and the fibula. All right. And then we have those weird little ankle bones in Tyrannosaurus Rex. They're above the ankle joint. In the birds, they're below the ankle joint. Same thing here. The one big difference is in the birds, a lot of bones fuse together. So it would start off as being separate bones fused together. So they, instead of having separate tarsal and metatarsal bones, they was called a tarsometatarsal. But my point is, birds are bipedal, just like we are. And just like, you know, that gives my hands, makes them free to do cool stuff. Their hands are free, but they've used it for flight instead. And that was the key. And so it was the dinosaur leg that lets it be bipedal, which then gives their descendants, the birds, this ability as well. So we see the same bones in the bird legs as we see in the dinosaur legs. And this was key to them developing flight. You have a question?
Oh yeah. So like the holes in the hip sockets, do they do anything or no?
And the muscles go through them. It's just a different way of getting a stable hip joint. Like we have a pretty stable hip joint, just orient a different way. But that's how they did it. All right. So if we were to go, actually, let me end with that. All right. So let's go here. So what makes a bird a bird? I asked you, you came up with a couple of traits, I came up with a couple of traits. There's a whole bunch of things that like for describe bird anatomy. Some of them start in the first amphibians, some of them start in the first reptiles. Those are those two temporal openings, etc. And so what we see here is like when we get to here, the ancestors of dinosaurs, the foot gets lengthened. What you're seeing is birds are built over tens of millions of years in stages. All right, birds did not appear. All right, so there are, you know, most of Earth's history had zero birds. There were zero birds in the Precambrian. The Paleozoic, half the history of vertebrates, has zero birds. The Triassic period, 50 million years from 250 million years ago, 200, has zero birds. But what you're seeing is that birds are built in stages. So I can show you a picture, I can show you the video, but here, for example, what does it take to make a theropod dinosaur? Let me go to this page. Because I know it seems weird, but there are rules, all right? If you find a bunch of dinosaur bones and you say, ooh, I want to say this is a dinosaur. I want to say it's a meat-eating theropod dinosaur. You can't just say that. There are rules. You just can't say, oh, look, these are dinosaur bones. These are meat-eating dinosaur bones. There are rules of what it has to have. If it has these things, it's a dinosaur. If it has these things, it's a meat-eating dinosaur. You just can't say it like, what do I classify that as? Call it a duck or call it a dinosaur. I mean, you can't say that. There are rules. What are the rules? Well, theropod dinosaurs have specific openings in their skull, the structure of the mobility of the lower jaws, a long neck, pits in the metacarpals, holes in the presacral. Here in red, these are the rules. But birds, at least the first birds, they have all of those too. So if you had a pile of bones and you're asking, are these dinosaur bones? If they have these traits, you would say, yes, it's a dinosaur, but birds have those. So you would say, well, birds or dinosaurs are meat-eating dinosaurs. All right. So there's this family tree of the meat-eating dinosaurs. All right. They're called the theropods. And then later, the family tree starts to branch. So we get subgroups. There's a lot of them. I give videos, you know, we'll just zip through this. And each of these are rules. What do you need to be a neotheropod dinosaur? There are rules. You just can't say this dinosaur is a neotheropod. It has to have these features. What rules, if you're a Tetanoran, there are rules. You have to have these features. And birds, at least the first birds, have all of these features, such as one of the things that's weird about birds is they have holes in their bones for extensions of their lungs. Birds breathe differently than anything else alive today. They're better, they're more efficient at breathing. And they have these air sacs going into their skeleton. Today, just like when you said feathers, it has feathers, it's a bird. We could say today, having holes in your bones for air sacs, that would be a bird feature. But it turns out this goes fairly deep down into the dinosaur family tree. That's a dinosaur thing that birds would later make use of. All right. Now, one big thing that you mentioned earlier was feathers. All right, so feathers, that makes the bird. All right, and when I think of feathers, I'm thinking of, here flying. It turns out feathers do a whole lot more than flight. I mean, notice the black and the white. All right, black absorbs sunlight and would have roles in absorbing heat. White reflects sunlight. All right, so just having black and white feathers would help you regulate your body temperature, even if we disregard flight for right now. Modern birds do it. So feathers have uses other than flight. Oh, and when you think about this one, if you've ever been in a tree that has parrots in it, like I am almost going mad. You think I'm exaggerating? I'm not. Because you're like, I want to go home and say I identified the parrots. And there's a million of them in the tree in Brazil. You can hear them, all right? But you can't see them because they blend in so well. All right, it's like your field guide, you got binoculars and you're like, there are parrots in this tree. There's a million of them. And then they fly and you're like, why couldn't I see any of them? So clearly the feathers are helping them hide. All right, so there's camouflage here. Or you have this. Here comes spring. You're going to have a whole lot of ducks on the same pond asking the question, who should I have sex with? Because a lot of them aren't the right species. And the females can look and say, oh, you're the ones with the green heads, or you're the one with the brown heads and the long tails. You got the white spot on your black head. And that helps them assort into the appropriate species. Here, a female cardinal could look at the male and say, are you well nourished? The better he is, the better his diet. So if the female's trying to pick the healthiest male for her offspring, feathers can do that. So point is, feathers aren't just for flight today, and they certainly weren't in the old days. Because if you look at this dinosaur and you look really close, it's fluffy. All right, it didn't have the scales that we associate with, modern reptiles. We have these fluffy things attached to them. This one has it. All right, there's a bunch of them that have it. This was actually the first one where it was definitely shown. And then it came to the Museum of Natural History. It was about 15 years ago. So like my students and a lot of people went down to New York. They were on tour. They actually got to see them. And so you can see that not only were some dinosaurs fluffy, a lot of them were fluffy. All right, it turns out like every year we're discovering more. And in Canada, there was actually some of these trapped in amber. So not only is there the impressions of dinosaurs being fluffy, there's actually these things. What do you call those? Some people would say, look, those feathers. Some people would say, I would prefer to call them proto-feathers. Some people would say, I would try to call them collagenous integumentary structures. And, you are free to call them whatever you want, okay? They are not the feathers that modern birds have. They are certainly not the scales that modern reptiles have. So they are somewhere in the middle. And what you call them whatever you like. But once again, birds did not appear suddenly with these feathers that no one else had. Feathers appeared long before birds. And the first feathers were not used for flight. But that's okay because feathers can be used to keep warm. Birds are warm-blooded, as are we. All right, and feathers help that. Feathers can be used for camouflage. Feathers can be used to attract mates or, for all sorts of things. And it seems how that is how feathers started. They did not have to start with flight feathers. Yes, you had a question.
I was going to say, did no one think that it looked like a bird? Like, it kind of looks like a bird too.
So, I mean, what this looks like it's structured differently. And I wasn't going to get into this. But so for example, there's different kinds of feathers. So here is a flight feather where there's the central rachis and the interlocking barbs. But then there's all sorts of other things. So this type of feather, right, this looks like a little more like hair than a typical feather, but it turns out like there's just different kinds of feathers. Like when you look at a baby Canada goose born, it's covered with down. All right, and so while it does, more superficially represent hair than say a flight feather does, when you look at it closely, there's difference between the hair that a mammal would have and then a downy feather. And for that point, like we have hair, I know we think that some spiders are hairy or some caterpillars are hairy. They're not. It's different. All right, so they've got spines over them that and bristles that look like hair, but under a microscope, and then we'll just start looking closely. Mammal hair is unique. Nothing else has hair that looks like ours. So here, like a central rachis, then it branches into barbs, et cetera. So here, birds are going to be at the top of this tree. But way down here, feathers appear. So long before there were birds, there were feathers. And if we were then to list the types of birds or the types of dinosaurs which have feathers, oh, I'm sorry. All right, it would be a long list. All right, so just zipping through. Right, so apparently downy feathers come first. And when you look at how birds develop as an embryo, from an embryo, they have these buds that will develop into a feather or a scale, but not both. So if you look on like a chicken, it has scales on its legs, which are like reptile scales. So these buds can become reptile scales, or they can become feathers. All right, and so it seems that a feather is a modified scale, and these embryonic buds then make a choice. Do you develop into one or the other? Now, once again, flight feathers can be extremely complicated. I'll talk about them. They have a central rachis, they have barbs, then they have interlocking barbules coming from them, but not all feathers are like that. So there are different kinds of feathers, which even in modern birds, like here's a feather, all right, but there are different kinds of feathers in modern birds. Yeah.
So fur is not modified scales because
correct.
It comes from a different soreness level.
Mm-hmm.
Okay.
And that's the and so as I talk about the evolution of birds, focusing on a lot of bones, because bones are easy to find in fossils. Some of these other things, like I could at the end mention, differences in the reproductive system, the urinary system, but we're just at that point just comparing birds to other animals today. We obviously don't have dinosaur urinary systems, et cetera. So a whole bunch of birds have fluffy feathers. Okay, but then just as a sample for your next, bio club party meeting or whatever. All right. Just don't your belly swollen, your feathers are symmetrical, your arms are short, your waist up right, your body's just not made for flight, body search, you can fly, but you have feathers, you can only fly. So there's that song. Then Microraptor has a song. Okay, but anyway, the point is, not only did some theropods have feathers, the fluffy downy feathers, then at some point, flight feathers evolved in dinosaurs. So once again, if you said, oh, look, this thing has feathers, it has flight feathers, it's a bird, that's true today. But in the fossil record, there were things that weren't birds that had feathers and flight feathers. Now, some of them might have been able to glide or fly, but Caudipteryx, so a lot of the birds that had flight feathers, all right, they couldn't fly. All right, so why were they using them? Well, I don't know. Was it for display to attract a mate? The ones on your arm, could it help you like scoop up like something that otherwise, you kind of form a basket that wouldn't something to get away from? Could it help you sit on a nest and warm the offspring? Would it affect mating, where you could say, these would have colors and they were effective in display? We don't know. All right, but we do know that flight feathers do not originate with birds. Here's Proto-Archaeopteryx, would have had flight feathers on its tail. DeLong, no, I'm sorry, that's just the regular fluffy feathers. Here's Caudipteryx, would have had flight feathers. This one you can nicely see flight feathers. Even things like Velociraptor, and this is where it kind of gets a little tricky. Sometimes you have impressions of flight feathers, but things like Velociraptor, do we have a fossil of Velociraptor that has feathers? We do not. But here's a cousin of Velociraptor that had flight feathers. Here's another cousin of Velociraptor that not only had flight feathers, we know what color they were. They were white, black with white stripes and some reddish ones on the head. But here's Velociraptor. Look at that dimple, that dimple, that dimple, that dimple. On modern birds, that's where the flight feathers attach. So not every fossil is going to preserve feathers if they were present, but the bones would have places where the feathers attached. From the evidence that we have, Velociraptor's cousins had feathers, and its bones are indicative that it did as well. Once again, here's flight feathers on a cousin of Velociraptor. This one didn't really have feathers, but look at those scales on the tail, just very long and branched. And so maybe that's where scales came from. All right, feathers came from that they were just long scales that then started to branch. Now, I've kind of skipped a couple of other things. Some of the theropod dinosaurs did this. There are two that we know that sat on their eggs. Once again, we associate that with birds, but theropods prior to birds were doing that. In the chest of a theropod, some of them had their clavicles fused. They had a wishbone. So wishbones we associate with birds. Some of the dinosaurs had that. Okay. And it wasn't as important. Some of them then started hips going backwards here in a way that we would share with birds. All right, so we see as we go up this family tree, so let me go to wherever it ends. For each of these groups, there are rules. You have to have these traits, all right? But it turns out birds fit in group after group after group until we get to wherever the last one would be. Okay. This is not the last one. But here, birds are going to be at the very end, I hope. Yeah, okay, there we go. So if you just classify things on objective and by objective criteria that you can ask, does it have this trait or that trait? It turns out birds nestle within the dinosaurs. Birds are dinosaurs. Like if I said, are these dinosaur bones? You said it follows the rules. These are dinosaurs. Are these theropods? Are these Technoran theropods? Are these Manicoran theropods? What follows the rules? Well, the first birds would be classified within the dinosaurs. They are neotheropods. They are Technorans. They are in each of these groups. So as of the middle of the Mesozoic, all right, if you were to look up in the air, here's the problem. The problem, luckily we didn't face at the beginning of class. You can look at a bird and say, or today it's a bird because clearly nothing else is like that. But here at the beginning, in the middle of the Jurassic, are those birds that look like dinosaurs, or are they dinosaurs that look like birds, right? They were so close that a lot of the experts have varied, and there have been things which have been first classified as a bird that are now a dinosaur, and vice versa. All right. Let's start talking about the wings briefly. Birds fly. They have wings. Yeah, what's a wing? It's a modified hand. So if we take the wing of the first bird, Archaeopteryx, and take its cousin, Deinonychus, that's a relative of Velociraptor, there's no bone of the first wing that dinosaurs don't have. They have this weird semicircular wrist bone that's unique to this group of theropod dinosaurs and birds. Numbers of finger bones that they have in the exact order, they're the same. The thing about the bird wings is they're a little bit longer. The theropod arms gradually got longer and longer. And so, that was something birds did. But, essentially there's very little difference between this hand and this wing. A wing is a modified hand. And so then come the middle of the Jurassic, for the first time in Earth's history, there are birds. There were no birds for most of the history of vertebrates. When the age of dinosaurs begins, there are no birds, but they're not crows or ducks or sparrows. Archaeopteryx is a bird. It flies, all right? Its feathers tell us that they're asymmetrical, where they're not equal on both sides. That's an adaptation for flight. But it's a weird looking bird. It's got teeth. It's got clawed, grasping fingers, all right? It's got a long reptilian tail. So the early birds are mixes of bird features and dinosaur features. One of the clear bird features that no dinosaur so far has is what's called a perching foot, where its big toe is reversed facing the other three. So 3 toes face forward and 1 toe faces back so that it could perch on a foot. So it's a bird, but it's clearly not a modern bird. Like, look at its skull, for example. So here, and I have this here if you'd like to take a close look at it. Here's the skull of the first bird. It's got features that remind me of birds that dinosaurs don't have. And if we wanted to talk about like this bone or that bone, but the fact that you can see where the bones separate from each other, the bird all fuses. Okay. The fact that you've got a hole here, no bird has that alive today. All right. In embryos, they start making this bone, but then this just becomes one big space. So that hole is something that reminds us of the reptiles. The birds don't have that hole today. This space fuses with the eye socket space. Obviously, it has teeth, and only mutant chickens have teeth alive today. So there is a line of chickens that have teeth. Here. And so while this is a bird, it certainly wasn't a modern bird. And, you know, these features of the skulls show us this. Okay. So birds exist, but they look like this, right? And it will take a long time before these birds are modified to be the birds that we recognize. So just like it took tens of millions of years to make birds out of dinosaurs, it will take 10 millions of years to make the birds that we recognize. One of the first things that happen is you have to lose that long reptilian tail. That's not helping yet. So one of the first things that happened before the teeth were lost, before the clawed hands were lost, is the tail shrunk to form what's called a pygostyle. And this happens in stages. So you go, you know, some birds, and so if you go to the Museum of Natural History, there's Archaeopteryx. That's a bird, but not quite looking like the birds of today. There are other birds that look like it with long reptilian tails. Okay, but one of the first things that happened is a pygostyle. So you go from a long tail to a longish tail, where some of the last vertebrae fused to one that looks like that. So that's the first kind of things that happens. So now you have birds that now have a pygostyle, but they still have claws on their digits. So this is a bird that comes a little later. It still has teeth. Interestingly, I mean, I know that looks like a tail. It's actually not. That's a feather. But it's a weird feather. It kind of looks like a scale. And so maybe, once again, this is where feathers came from. You just make really long scales that get fluffy. And so then maybe this kind of a version of that. So this is a bird. And, you know, I like it. It's a cool bird by all means. But they're not good at flying yet. Okay. And so then tens of millions of years after the first bird, there's going to be a change in what's called the thorax region. Birds get a different thorax, a chest, and it turns out that makes all, it makes all the difference. And I apologize, having so many videos. There we go. Yeah. So then the first birds, they weren't good flyers. Like they probably couldn't take off like this the way a modern bird. They'd probably have to get a running start or like jump out of a tree and go flapping like this. So birds today are really good flyers. The first birds weren't and spent millions of years not. Yes?
You're saying that they have to jump out of a tree, but would that be a combination of both running and jumping out?
I mean, depending on how high the tree is, they like catch you there and jump in there.
Well, yeah, but my brain's like, would they be able to climb the tree?
Well, so
they, like,
so I want to say, I could tell you my guesses. The difficult thing is here, you're asking a question, and the only way to answer in a scientific sense with evidence is like to be able to observe it, you know, which I can't. Like, so some of them were really small, like Microraptor could have fit into the palm of your hand, had claws that could climb. So you know, there would be nothing that would stop it from being a good climber. But I apologize, you know, other than that, it'd be.
I'll read with the ones that you were just showing us. I forget the names. Yeah.
Smaller than a turkey, bigger than a crow.
Yeah, I thought it was like huge. I was like, huh?
Yes. Yeah, so actually Velociraptor is a cool name. In the movies, they're really using Velociraptor's cousin Deinonychus, which was a bit bigger. So modern birds, they have problems on their ribs help anchor them and give them more stability. They actually have a set of ribs where it's not only they have going down, they have ribs coming up from the sternum as well, called sternal ribs, etc. And so you can see these in modern birds. This is their thorax is different. Another thing there, so two more maybe three. They do something. Here's the ingenious thing. Oh, this is really makes flight good. So obviously, if you want to pull your wings down, all right, where would you would use chest muscles. So birds are going to start with bigger chest muscles that pull the wings down. But the hard part is going to be also then pulling it up. How do you do that? Well, you could put a muscle on the back, but now that throws off your center of gravity. Now you have a big, heavy muscle above your center of gravity, which would affect how it would affect your flight. So what birds do, the muscles down here pull the wings down, and underneath that are muscles down here which pull the wings up. How can you pull the wings up from underneath? Well, because the tendon of this supracoracoideus actually will then go up over the shoulder joint through a hole, all right, called a triosseal foramen. Three bones come together to make a hole, and the tendon of that muscle goes through the hole. So while the muscle is below, the tendon goes up and attaches to the wing from above to pull it up. So birds don't have a big muscle above them, which would make flight harder. It's actually beneath them affecting the center of gravity. So here is where the scapula, the clavicles, the furcula, and the procoracoid come. There's a hole, and there's a tendon of the muscle which goes there. So that came, later in the late Mesozoic. The breastbone started off flat. All right, T-Rex had a flat breastbone, but flying birds get a keel, get this big attachment for flight muscles. That doesn't occur in the first birds or even Confuciornis of the Cretaceous. That develops later, this big keel. Now, obviously, birds don't need that because not all birds are flying. So if you were to look at an emu, here you can see its sternum doesn't have a keel. All right, so it's not a definition requirement for birds, but once birds do this, they have much more room for those flight muscles. Okay, so in the middle of the Mesozoic, the next group of birds, they're changing the chest, they're changing the shoulder girdle. All right, and the shoulder girdle is now like these three bones. There's the furcula, the two clavicles which fuse there that act like a piston, the procoracoid, and the scapula. And the scapula strap like it looks a lot like a reptilian one. And this then is the shoulder for flight, is a modified shoulder that the dinosaurs already had. All right. One other thing that they're going to do is eventually they're going to lose their teeth. Because once again, if I'm trying to fly, I've got big teeth. That's just putting something heavy at a place where I don't need heavy. So what do birds have? A gizzard that grinds their food. That's here. So what birds do is they move their center of gravity, all right, so that they don't have a long tail going out this way. They don't have heavy teeth up this way. They don't have big muscles on their back. This is their center of gravity. Their gizzard is here grinding food. The muscles which pull here on the chest are down there. And so they just reoriented their body, making it easier for flight. Let's go to the wings, bones. The bones that you find in an avian wing, and we would know this from eating chicken wings, they're just the same bones that you have. They have the procoracoid, which mammals have lost, the scapula, the clavicle, making the shoulder. Then there's humerus, just like I have. They have a radius and ulna, just like I have. They have some carpal bones that I have. And then they have the remains of 3 digits, these modern birds. The earlier birds had more, and they had claws on their digits, but these birds still do. Claws on the digits would actually stay for a while. And actually, the emu, who gave those bones, had a tiny little claw on its arms. Herons have tiny little claws. And here's a bird in South America that obviously has big claws. All right, so claws at the tips of the digits, while most birds have lost them, a few still have them. Chickens still have the ability to make teeth. All right, and so, you know, along the way, all the early birds had teeth, or almost all of them had clawed digits, and this would change. Just like birds modified the existing bones to make wings, then they modified existing muscles were already there. So birds have a biceps. Birds have a triceps. So when you eat, you know, chicken wings, you're eating homologs of the muscles which you have. Okay. As we start going up the family tree, there are two big groups of birds in the Mesozoic. One of them becomes extinct and one of them survives. So the extinction that wipes out the dinosaurs, just as it wiped out the dinosaurs, it wipes out the most common birds of the day. The lineage which we have starts fusing bones together. So they fuse their sacral vertebrae and their hip together. That makes a synsacrum. They fuse the tip of their tail to make a pygostyle. They fuse their ankle and toe bones to make a tarsum and a tarsus. They fuse their wrist and finger bones to make a carpometacarpus. So when we look at a bird skeleton, we see lots of fused bones. Right around when the dinosaurs died, that's when the first lineages of modern birds started. All right, now we could argue, did they start right before the line or right after the line? That would be a fight. And so let's not get into a fight. So it was either right before or right after. Bird fossils are kind of hard to identify. The most primitive group of birds alive today are the flightless ones, the ostrich, the emu, the rhea, and also some birds which can fly in South America called tinamous. So they are called the old mouth birds. The roof of their mouth has a more reptilian shape. So that's the most primitive group of birds alive today. They have the old mouth. And if anyone really wants to know what's old about it, I have a video on that if you really care. All right. And then the new mouth birds, which make up most birds alive today, all right, they start branching. The most primitive branch alive today are chickens and ducks. Chickens and ducks, all of the molecular studies put together in a group. All right, so chickens and ducks, we could argue, did they start right before the dinosaurs died at this line or right after the dinosaurs died at that line? All right, I'm sorry? Yes. So we could ask, you know, like this, you know, fossil here, you know, is it the duck-like one, which has its long legs, et cetera? Sometimes genes suggest older dates for divergence compared to what fossils actually show. So we could argue, but the point is, it wasn't until the end of the age of dinosaurs or just after that that we start to get groups of birds alive today. Now, when the dinosaurs died, one thing that's obvious is all of a sudden Earth lost its big predators. So birds were the first ones to take were to change this, right? So that today we know that there are lions and tigers and bears and the like. But when the dinosaurs disappeared, then there were these birds which would have, you know, 6 feet tall, 9 feet tall, skulls the size of horses. For a while, birds were the dominant predators on Earth, and mammals were these little things running in fear of them. Then as the age of mammals progresses, then we start to see lineages of birds of the ones today. So these all evolved gradually. Before there were woodpeckers, for example, there were woodpecker relatives, which had some of their features, but not all. The earliest ducks had really long legs. The vultures of today come from two different groups. The New World vultures, some of them had 26 wingspans in South America, like 18-foot wingspans in North America. They were called the Teratorns. The early hawks and vultures still had long legs, as does the secretary bird, which is alive today. The early penguins didn't look much like penguins. They had to be modified. And so birds slowly developed. The last big point is that when we think of birds alive today, The ones we think of most are the most common ones, the songbirds. They're little, they're colorful, they make nice songs using something called a syrinx. But that's the last group of birds to evolve in the family tree. So the order Passeriformes that has the songbirds, the pretty ones that make the calls, they don't exist at all in the age of dinosaurs, nor in the early age of mammals. It would be midway through the age of mammals in the Miocene that we get them. So a couple of points. Birds outnumber the mammals, reptiles, and amphibians put together. So if you count numbers of species, if we're asking who's doing well on land, in terms of numbers of species, the birds have more species than mammals, reptiles, and birds together. So birds are doing great. And if they are modified dinosaurs, which all of the evidence certainly seems to indicate, that the age of dinosaurs hasn't really ended, that dinosaurs would still be the most numerous species alive today. So there's a whole lot more that could be said. I have on my YouTube channel, separate playlists on the songbirds, the hawks, the eagles. But as far as the evolution of birds, I think that's the picture. If anyone at the end, I know the club has to settle some details, but we have bones up here like the synsacrum of bird. This is where the hip, the vertebral column, etc., are fused. You can very delicately handle the skulls of birds and see how different they are. We have a couple of those, and we have the rib cage of birds, and a bunch of the emu bones here. So I'll be happy to answer any questions, but I don't want the biology has some important discussions to make, so let me stop there. Thank you, Natasha. Did you have any questions, Natasha, real quick?